the midterm. So this week we are still going to do the midterm review and rereading for during the PSO sessions. So if you have any questions, go to the PSO sessions. Pay attention to which TA is responsible for which PSO session, because you need to be, if you want to ask for reread for question 1, for example, you need to go to the TA who graded question 1. Right? Go to that PSO session with TA who graded question 1. And I know some students have been sending me emails about regrading requests, and we have been collecting these questions, so I'm not responding right now because we're collecting these questions and we'll respond to them together. Just to make sure that we have a consistent answer to all the regrading requests. Right? So we want to have a consistent policy for all the regrading requests. Okay. All right. So now let's go back to the lecture content, and I think the last lab has been released, right? So hope everyone started working on it. And file system, right? So we were talking about file system consistency at the end of the previous lecture, and we explained the simplest version of a file system consistency issue, and also how to recover from it. Yeah, so anyone remember, right? What is a file system consistency issue? How did it happen? Right? How does it happen? Right? It can be caused by a crash. Okay. We used some simple example to explain why a file system crash could cause a consistency issue. What is a consistency issue? Yes.
If I remember correctly, it was because the RAM had changed some things about the file, but didn't get to change it on the disk, and the RAM doesn't save anything between rebooting or the computer's turned off.
That's very close. That's very close. You're on the right track. So the RAM, for example, if you are modifying a file or creating a new file, everything is still in memory, and your computer crashed, everything is lost. Does that cause a consistent issue? No, you have to, the file system operation, the create file or write to file have to finish partially on the disk, right? So what you said is correct. A file system consistency issue happens when you have a file system operation which involves multiple steps, right? Such as when you create a file, you need to create a seek to that directory, add this directory entry in that directory, create inode, and write some content in the first block of this file. And this series of operations, they will first land in memory, and then they will be flushed to disk, right? If unfortunately some of these operations, maybe the first operation landed on disk, but the remaining did not, this will give you an inconsistent file system. Right? You could see that, okay, my directory entry has this pair, has this file, it links to an inode which does not exist. Right? That's an example of inconsistent file system. Right? Because the inode you created did not get flushed to disk. Right? The directory entry got written to disk, but the inode did not get written to disk. That's how an inconsistency happens. Okay? All right. We explained the simplest version of file system inconsistency and how it can be resolved. The simple version of file system inconsistency we explained was a missing block. Right? So remember that a file system has a list of 3 blocks which are not allocated to any file, and the remaining blocks are allocated to each file, organized in their inodes. Right? Inode is an abstraction of is a approximation of a linked list of all the blocks belonging to a file. Okay, so when you allocate a block to a file, you need to take this block out of the free block list and insert this block into the inode of a file. At least 2 operations. Right? If unfortunately the file system crashes while you are doing these 2 operations, right? Maybe you take that block out of the free list and your file system crashed. That block was not added to any file, it's just lost. It does not exist on your free block list. It does not exist in any files inode. Okay? This is the simplest version of file system inconsistency, and the solution is simple. Right? We explained that you can iterate through when your computer restarts, and this is typically automatically done. Right? When your computer restarts, it will scan or iterate through the blocks of files and iterate through the blocks on the free list. Right? Scan all the blocks on the free list, scan all the blocks belong to each file, and it could, because of this, it could find there is some block that does not belong to any list. Some block does not belong to a free list. It does not belong to any file either. Okay. Once they find this block, the solution is simple. Just add this block back to the free block. Right. This is the simplest inconsistency. You could also have other inconsistencies, like a block exists is duplicated, exists both on the free list and also on the list of some file. Right, so and this scanning could also help you find that. Right. Yeah, you can have a missing block. Right, you don't have the block in either the free list or any files list, and or maybe it's also possible your free list contains the block twice. Yes, you can get rid of one of the block. Right? And you can also have some block that's present in multiple files. Okay. And the solution is simple: allocate a free block and duplicate. Right. Okay, so this is a simple version of file system consistency, and then let's look at more advanced version. So this is a slide that borrowed from the University of Wisconsin-Madison's file system operating system course. Right? So they have a more detailed explanation of journaling, which is an advanced technique to resolve file system consistency. And I do still recommend that if you are interested in operating system, read their textbook. And that operating system 3 pieces, 3 easy pieces. That's a very good book to read. Okay. All right. So the slides start from file system consistency, which we already explained. The issue is straightforward. Right? So we'll quickly go through this again. Right? So every file system has a super block. This field contains the total number of blocks in the file system, and maybe also the root directory of this file system. Right? That's a super block. Right? Every file system has a super block. And inode, right? So we explained what inode is. Right? Inode contains a pointer to the data blocks that belong to a file. Okay. Again, the file system consistency issue arises because a file system operation will perform several disk writes to redundant blocks for one operation. Create a file, move a file from one directory to another directory. Right? Many of the operations that user perform, from user's perspective, is just one operation, but at file system level, it's actually multiple disk writes. Okay, if these multiple disk writes were interrupted by a crash, right? Only part of the finishes, the remaining did not finish. These will result in file system inconsistency. Okay, right. So if a file system interrupted between writes, right, so it may leave the data in an inconsistent state. Okay, so a crash could happen because of power loss, because of kernel panic, right? Your OS just crashed, or manual reboot, right? Even actually, I'm not sure whether you guys experience. I think nowadays, do you still reboot a computer very often? Still? Okay. I think I remember when I first started using computer, that was around 2000. Right? So even before that, maybe 1998, around that time. There was we have computer labs, and the computers are shared by the students, and we have this rule. I think nowadays the computer labs, they don't have this rule, but we have this rule that you should not reboot your computer. Right? Students are banned. The teacher, they can do that, but the students are banned from rebooting their computer. And the reason is because in the early days, there's very less protection of the file system's consistency. And if you just randomly reboot your computer, it could cause the file system to be inconsistent. Right? In the very early days. And there are a lot of interesting rules in the early days. This is avoid rebooting your computer, that's one. I remember another thing is that I'm not sure whether you have you experienced. I was requested to wear this kind of special socks that's outside of my shoes, so that I do not bring any dust into the computer lab. Right? So that was also in the 1990s, very early days of yeah. So there are a lot of rules. Right? Nowadays, computers are more robust. They are not that easy to crash and become inconsistent. Okay. Yeah, but I think still, right? So I'm not sure whether you have heard about this more advanced computing labs in Google and Microsoft. For example, those labs that they are working on quantum computers. Right? In those labs, you still need to wear special socks and even special clothes in order to enter those labs. Right? Have to. Those computers are still very unreliable at this point. Okay. Yeah, just some side stories. Right? So this is how a file system looks like. Right? So you have a inode map, you have a data block map, and then you have the blocks that are really storing the inodes, and you have the blocks that are really storing the file system data, right? The data content belonging to each file. Okay. At the beginning of the file system, you have bitmaps. Okay. All right. You can imagine, right? So when you create a file, you need to touch these multiple locations. Right? You need to create an inode. Right? You need to allocate data blocks for a file. You need to because you need to create an inode, you need to change this inode bitmap. You also need to allocate an inode for this file. And because you need to add data blocks for this file, you need to change this data block bitmap. and you need to allocate this data block for the file. Right? And also, once you created this file, you need to add this file in under some directory. Right? So you need to modify that directory, its file content too. Okay. Right. So these this shows there are multiple disk locations you need to modify whenever you perform a file system operation. Okay, so how do file systems fix inconsistencies? Right, so we already explained the simplest version of file system inconsistency problem is when you have blocks that are lost. Right? And FSC key or file system checker fix these kind of simple consistency issues. Right? What does it do? After crash and reboot, it scans the entire disk, right, for contradictions and fix the contradictions if needed. Okay, and this means that when you restart your computer, it will take a while to scan your disk, right? So this takes some time. Right? Yeah, how to tell a data bitmap block is consistent? You read every valid inode plus indirect block, and you pointer to a data block. The corresponding bit should be 1, else the bit should be 0. Right? You check whether this data is valid. Okay, this is very straightforward. Right? So it does perform a list of checks, right? Not just that one. Right? And it checks whether the super blocks is still valid, whether the list of free blocks is correct, whether you have any block that's not on the free blocks and also not belong to any file. Right? Do number of directory entries equal inode link counts? Right? Do different inodes ever point to the same block? Are there any bad block pointers? And do directory contain dot and dot dot? Right? So these are an incomplete list of the file system checks that are performed. Okay. Right, so free block example, we already explained this. I don't think we need to spend time on this. Right. A link count example, right? So inconsistent could happen when you have 2 directories that have hard link to an inode, but the link count is 1. Right? This probably is a result of an incomplete remove or delete operation. Right? So the remove or delete operation decremented the link count, but did not really remove the link from the directory to this inode. Okay. Duplicated pointers, you have 2 files pointing to the same block. Bad pointers, you have a pointer pointing to some corrupted data. Okay. FSC key is not perfect. It has problems, and because of these problems, we want more advanced techniques. Right, so here, problem 1, it's not always obvious how to fix a file system image. Right. The previous examples we have seen are relatively straightforward. You kind of know how to fix it. Right? If a block does not belong to the free list or any file, then you add it to free list. The fix is relatively straightforward. But there could be complicated scenarios, right? Very weird consistent issues whose solution is not very obvious. Okay, you don't know the correct state, which is the correct state to recover to, and yeah, you just saw that this state is inconsistent, but you don't know what is the correct state. And the easiest way to get consistency is to reformat your disk, but this causes you to lose all the data on the disk. Okay. And the second problem is that the FSC key is very slow, right? You need to scan all the blocks on the disk, And if you have a huge disk, it takes a long time to scan it, and it means that every time you reboot your computer, it takes a very long time. Okay. Right. So if you have a 600 gigabyte disk, it takes over an hour to scan it. Right. All right. So this leads us to the more advanced solution, which I think nowadays is a very it's widely adopted. Right? So every file system has journaling, and it's not even it's actually a broader concept, not just limited to file system. It's also used in database for database transaction, right? And it's also used in cloud system, right? In many softwares. If you want crash consistency, you use this technique, journaling. Or in cloud system, they call it the write-ahead log. In a database, they call it usually also write-ahead log for transaction. Okay. So the idea is very simple, right? The idea is very simple. So because file system inconsistency is caused by you have a list of operations, right? File system writes to disk, but they only finished part of them, right? That's the reason of the inconsistency. So the solution, journaling, means that I just log these a few file system operations, right? Suppose I want to do 3 file disk writes, and log these three file disk writes before I really do them. Right? So I know which was the operation I plan to do, and if a crash happens, I know which operation I finished. Right? After I finish one operation, I will just add a flag, the first operation finished. After I finish the second, and flag the second operation is finished. Right? After every operation, I add one flag that this operation is finished. Okay, so if the file system crashes, when I restart my computer, I can check the log, see where I crashed, and continue execution. The solution could be I continue execution, finish the remaining of the operations. Right? The third operation I did not finish, I will just finish the third operation for them. Right? Or some other technique allows to roll back. Right? So you have the rollback operation defined for each operation. Then if you see, okay, I didn't finish these 3 operations, I just perform rollback. Right? So those are different techniques. But the key is that you need to have a journal or what they call write-ahead log to log the operations that you want to perform. And when the crash happens, you can examine this log. Right? After you recover, you can examine this log to see where you were before the crash. Okay, that is a high-level idea. Now let's go through the technical details. Right. So yeah, we want to do some recovery work after crash, but we do not want to scan the entire disk, right? So this is to avoid the performance overhead of FSCK. Okay, and a second goal is that we do not want to move file system to just any consistent state. For example, I don't just want to reformat my entire file system because I'm going to lose all my data, right? But I want to move file system to get the correct state that was intended before the crash. Okay. All right. So to achieve this, we have some formal concepts we need to define, like atomicity. Right? I think atomicity is a very common concept you will run into in different computer science courses, right? Such as database. So this is a very often mentioned in database because database transactions need to satisfy ACID properties, ACID properties. Right? A represents atomicity, C means consistency, I means isolation, D means durability. Right? Okay, so this concept of atomicity appears in different computer science courses, but the definition, the formal definition varies slightly in different contexts. Okay, in OS or in file system, atomicity has this definition, right? Definition of atomicity for concurrency, it means that operations in critical sections are not interrupted by operations on related critical sections. Right? This is the concept that you are familiar with when you study the synchronization mechanisms, mutex and semaphores. Right? So inside the critical section, all the operations are executed together. They should not be interrupted by other operations from the other related critical sections. Right. Now, the definition of atomicity for file system is slightly different. Right? It's atomicity for persistency. Right? What it means is seeing that there is a collection of writes that are issued by one file system operation, such as create file. Right? They are not interrupted by crashes. Right? They either all is visible, all are persistent on disk, or either all new data are visible on disk, or all old data is visible on disk. Okay. So that is a definition of atomicity for persistency. Right? You have a collection of writes that semantically it belongs to one file system operation. Okay, and they are not interrupted by crashes, meaning that even if a crash happens, really happens, right? It does not either the effects of these writes either do not show in the disk, or all of them should show, be visible in the disk. Okay? Right, does it make sense, right? The definition of atomicity. All right. Okay, the relationship between consistency and atomicity. Right? So you see that there is a set of writes moves the disk from state A to state B, right? And this is from state A. Sorry, let me see. Yeah. So this is a set of writes, for example, generated by creating a file. Right? It moves the disk from state A to state B. Right? Here it means that state A is the state of the file system before this file is created. Right? State B, right, concretely, this new file should exist, should have been created on the disk. Okay, just making it more concrete. Right? So in this diagram, you will see that this represents all the states of the file system, and this gray area represents the consistent state of the file system. Okay, and that yellow circle represents the empty state of the file system, meaning that this is a state that your file system is in after it just gets reformatted, the empty state. So A and B represents a state where this file is created. A represents the file before the file is created, B is after the file is created. Okay, and the difference between FSCK and journaling is that FSCK gives consistency, meaning that if a crash happens in the middle of these writes, FSCK is free to recover the file system to any state in this gray area. Okay, it might recover it to this old state A, it might recover it to even the empty state. Any consistent state is acceptable to FSCT. Right. In comparison, write head log or journaling, which guarantees atomicity of these writes. Right. It gives you A or B. Right. Atomicity says that this set of writes, either all of them happen or none of them happens. Right. So, which means that after recovery from the crash, your system is either in state A or in state B. Okay, that's the difference between consistency or consistent state and atomicity. Right. So atomicity of writes is what people want. Right. It's a better goal. The technique to achieve atomicity is journaling. Right. So in this diagram, you'll see that every file system now has a journal. Right. Have a section that is on the file system that's used just to record file system journal. Right. The old file system still look like this, but now you have transactions. Right. Each transaction is a set of the writes that belong to one file system operation, right? Or it's a unit of atomicity. Okay, the writes that belong to one transaction, right, here, right, I'm going to write this inode block, right, this data block, this bitmap, right? These are 3 modifications to the file system on disk. These 3 writes are grouped in one transaction. The meaning, right, the semantic is that these 3 operations, they should either all of them happen or none of them happen. Right? That's a concept of transaction. And this transaction is what's recorded in the journal. Okay. Before these operations, I suppose I have this transaction. I want to issue to my file system. Before any of these modifications are really issued, I need to log them inside these transactions, right, in the journal. After I finish adding it to the journal, that's when I can go ahead and execute every one of them. Okay, does it make sense? Okay, let me see. So actually, I think let's pause here a little bit. Right? I think the remaining slides are explaining more advanced techniques. But here we want to focus on explaining this specific technique clearly. Right? All right. Yeah. So can you imagine one question? Right? Each of the operation of the writes that is included in this transaction, there is a special property that is that has to be satisfied. Right? Each of these operations. Can you guess what it is? So these writes are not arbitrary. Right? For example, let me see. Yeah, I think there are different techniques. I just want to explain the simplest one. Right? So in the simplest version, you can imagine in the simplest version of this transaction log, each operation should be idempotent. Right? That's what they call it. which means that you can execute this operation multiple times, but the result will be the same. Okay, what is an example of an idempotent operation versus a non-idempotent operation? For example, if you increment some value by 1, that is not idempotent, because if you execute this increment twice, you will on a value 0, you get 2. Okay, so you apply it once, you get 1. Apply it twice, you get 2. That is not idempotent. In comparison, an operation like I'm going to modify a value to be 1. This is an idempotent operation, because no matter how many times you execute this operation, the result will be the same. Okay, the simple design of the transaction is to require every single every single operation in this transaction to be an idempotent operation. Okay. I'm going to overwrite this V2, this block, with some content. Okay. I'm going to overwrite this, so this, this idle bitmap V2. Right? This is a data bitmap V2. Right? So with some content, right? Value 1. I'm going to overwrite this data block with some content. And these are all idempotent operations. Okay, now imagine why this makes it simple. Why this makes the entire journal file system or crash recovery using journal file system easy.
Like probably like if it wasn't idempotent, then if it crashed, then it could like apply it to be like a different value, right? But if it's idempotent, it would be like the same, even if you like have to apply it again.
Right, exactly, right? So if it's idempotent, after crash, all you need to examine is whether this transaction finished before the crash. Right? So every transaction, after you finish all the operations, you will add a flag saying that this transaction has been finished. If after you recover from crash, you see that this flag is not set for this transaction, you know that this transaction is not finished, and if every operation in this transaction is idempotent, you just re-execute all of them. Right? That brings your system to the desired consistent state. Okay. Right. If it's not idempotent, you will have trouble. Right? So you don't know which part of it can be replayed, right? And if you replay some operation, the operation was executed before, and you replay it again, you will get inconsistent results. Okay. All right. I hope this is clear. Right? So this is I explained one of the simplest implementation of journaling using transaction and how it can be used to do crash recovery. Right? If you have transactions, every operation is idempotent, and after a system crashes and it recovers, you just check which transaction is not finished and re-execute all the operations inside the transaction. Okay. Right. It will be interesting. So there are a lot of more advanced techniques to make file system journaling have a better performance, for example. But this is the simplest one. Okay. So checkpoints. Right? So you have a journal, a log of all the transactions, But very often you do not want to keep the entire history of of all the transactions that happened from the beginning of time, right? So that's why you want checkpoints. So let's explain what checkpoint is, right? So some example transaction, right? Write A to block 5, write B to block 2, and sorry, let me see. Sorry, I forgot what this is. I forgot what this diagram means. Just 1 second. Because this is not what I remembered a checkpoint is. Okay, so I don't think this is what I remember, but I'll explain what checkpoint is without using this example. Okay, so all right. The concept of checkpoint is very simple. If you you want to remember a recent consistent state, right? So that's where you can start replaying the transactions. Okay. Let's start with the simplest example. Suppose your file system crashed. Okay, your file system crashed. Right. After recovery, because of crash, your file system could be in an inconsistent state. Okay, and the simplest solution is if you have all the transactions recorded from the beginning of time, from the empty state of the file system, and you replay these transactions one by one. Okay? You replay all these transactions one by one. All right. Then you will reach the consistent state that you want to reach. Right? This design allows you to have non-idempotent operations in your transaction. Now you have a checkpoint. Yeah, so this is using checkpoint is a more advanced technique, right? You have a checkpoint which you are sure is a consistent state, and you start from that checkpoint to replay the transactions that have been added to the log since that snapshot or since that checkpoint. Right? Because you know that checkpoint is consistent, so replaying the transactions starting from that point will give you a consistent state. And this design allows you to have non-idempotent operations in the transaction. Okay, and you want to do this create checkpoints periodically, because if let's say your checkpoint is just the beginning of time, the empty state of the disk, then every time after you crash and recover, it takes a long time to replay all the transactions in history. Right? So periodically, you will do a checkpoint. You have a checkpoint operation, and when the checkpoint operation is issued, it will make sure that all the transactions are delayed. Right? So I'm not exiting any transactions. Right now, I'm only checkpointing the state of the file system, and make sure that the consistent state of the file system is checkpointed. Okay. Once this is checkpointed, a consistent state is checkpointed, all the transactions before this checkpoint can be thrown away. And you need to only keep the recent transactions after the most recent checkpoint. Okay, does it make sense? That's a high-level idea of checkpoints. I don't remember exactly what they are trying to show here, but yeah, checkpoint is to record the most recent consistent state where you can start replaying the recent transactions. Okay. Yeah, so a few ordering guarantees that are needed in order to make sure the journal file system works correctly. So there are a few barriers that are placed in the file system journaling operation. The first barrier is before journal commit, ensure that the journal entry is complete. You need to make sure that the journal entry, which is the operations inside each transaction, they need to be written into the journal. And then after you write the operations of each transaction into the journal, that's when you can see, okay, journal commit, or you're committing these transactions in that this transaction is committed to the journal, right? We will execute this transaction. Okay. And the second barrier is before checkpoint, ensure the journal commit complete. Right? So your checkpoint essentially needs to be an atomic operation. Right? So all the transactions that you have issued need to be paused. Right? They either need to be finished before the checkpoint, or they need to be delayed after the checkpoint. Right? This is the point. Right? So all the journal commits, all the transactions, they need to be committed to the journal before you start doing checkpoints. Okay, right. And the third barrier is before freeing journal, right? Before you delete and free the transaction from the journal, right? Ensure in-place updates are complete. Ensure those each operations in the transaction has been finished. Okay. Right. So these are the barriers that have to finish in order for the journal to work. Okay. Right. Okay, checksum optimization. There is a checksum stored with each transaction block to avoid data corruption, right? Because in these hardware devices, right, in memory or in disk, these data corruption often happens. Right? Although I think as a user right now, you do not often experience it when you are using your laptop, but that is because these hardware errors are masked by low-level redundancy. Right? It's not that they do not happen. Right? The data corruption, right? Bit-level data corruption happens all the time in everyone's computer. Right? You do not see it just because they are masked by hardware and software mechanisms. Okay, one of the popular technique to mask to detect data corruption is to use checksum. You create a checksum of a data block, in this case a transaction block, right, as a proof of the integrity of this data block, of this transaction block. If any part of the transaction is corrupted, you can run the checksum computation function again, and you will get a checksum that is inconsistent with the checksum that you are stored. Okay. Right, so that is how we detect the data corruption. When you first construct a transaction block, you will also construct a checksum, right, using the checksum function, right, typically some type of hash function. And later, when you replay the transactions in this block, you need to first check the data is not corrupted by computing the checksum again from the transaction block and comparing the checksum that you computed against the checksum that was stored together with the transaction block. Okay. Yeah, I'm sure that most people have experience, have used checksum, right? If you have downloaded, for example, the image for Ubuntu or for any Linux distribution, to install a Linux distribution yourself, right? Usually, after you download the Ubuntu's image, it also comes with a checksum that you can use to verify the integrity of this image. Right. So, sorry. During recovery, right, if the checksum does not match, it means that some transaction might have been corrupted. Right? And if there's any transaction that's corrupted, you should not replay it. Right? You replay it, it would cause corruption. You should just drop that transaction and stay on the safe side. Okay. Right. So checksum to protect the integrity of the transactions. Okay. Other optimizations, batch updates. If two files are created, and inode map, inode get written twice, you mark dirty in memory and batch updates. Why this is optimization? And because inode bitmap and data block bitmap, these are very small blocks that probably are mapped to one or two pages, the same page probably in memory. Right? So if, for example, maybe you have created two files, and you need to add inode for them. You need to modify the inode bitmap for them, and their inode bit might reside on the same page in memory. Right? So if you batch the updates, you are for the creation of these two files, you are just writing one page, and that's the performance benefit you can get from batching. Okay. Batch a bunch of file system updates together, you will have a better throughput. Okay. Another optimization, circular lock, right? So you can start from transaction 1, transaction 4. You just keep appending transactions at the end, right? And if the you have reached limit, you just append the transactions from the beginning. You overwrite the old transactions. Okay, as long as the checkpoint has already been created for this transaction. For example, if you have a transaction, have a checkpoint created here, then you are free to create new transactions that overrides T1 and T2. Right? That is a circular lock. How to avoid writing all this block twice, right? There are some other optimizations, right? So because most writes are user data sequential writes, so the strategy is that you journal all the metadata, and, including superblock, bitmaps, inode, indirect blocks, directories, right? These are all the metadata operations, And for regular data, write it back whenever convenient. Right? So you don't really write the data back. You only write the journal the metadata and write them back. Right? So this is still batching, right? But a more advanced version of batching. Let me see. Okay. This is one example, right? I think it's to show that crash does not affect the correctness, right? How does journaling guarantee consistency during a crash, right? So let me see. Right. So in this transaction, we have a transaction that modifies the bitmap and inode. Right. And so when we execute this transaction, it will cause append to inode I. Right. So maybe because I want to add a data block to this file, I'm going to append some data block to this inode I. Okay, and at this point, if the crash happens, and it means that maybe part of the metadata is not updated. Okay, and when this happens, how do we address this? How do we address there is a crash that happens in between the metadata operations? Sorry, let me clarify. I think maybe I did not explain this clear. Right? So the solution is very simple, right? So the point here is that maybe explain the solution first, might make it easier. Right? So it's not very different from what I explained. The point is that for any file system operation, it involves metadata operation and data operation. Right? And the solution here mentioned is okay, I'm going to write the data content first. I'm going to write the file content that's needed for this new file, for example. I'm going to do that first, and then use transaction to finish the metadata operation. And why is that? Why is that a acceptable solution, right? So for the crash? Because file system consistency is really about metadata. If you lose a block, if you craft a block, a data block, here and there, you lose a block, and or if this data block's content is messed up, that can be easily recovered. What is hard to recover, what is hard to get correct, is the metadata. Okay, so you put all the metadata operations inside the transaction. Make sure that these transactions, metadata operations are actually correctly, consistently, atomically. But for data operations, you can just execute them outside of the transaction and write the data operations first. Write the data content first, and then use file system journaling to execute the metadata operations. Okay. so a summary of file system consistency, right? The problem is crash consistency, right? This is a problem that existed since the beginning of OS, or since the beginning, I think probably 1980s, right? So not very beginning, but very early days of operating system. So it has been there for almost half a century, but it's still very hot research topic until even until recently. Right? If you search on the top conferences using crash consistency as keyword, you will still find many research papers on crash consistency, and it's still a very important topic. Okay, and there are two main approaches. One is that you do a scan, you do a file system check, and you identify potential inconsistencies, and you bring the system to any acceptable consistent state. The second solution is journaling or write-ahead log. Right? So you write a transaction before updates, right? Before in-place updates, and then you replay this transaction after crash. Right? You replay the transaction from the most recent checkpoint after crash and recovery. And there are many optimization techniques, checksum, batching, ordered journal optimizations that can be applied to reduce the overhead of journaling. Right? So actually, I think one thing we did not mention, we were always seeing good things about journaling. What is the downside of journaling compared to FSAK? Yes?
It takes longer to write.
Takes longer to write, yes. So it impacts your normal file system operation, right? FSAK, it's only done after your file system crashes. There's nothing that you need to do in order to use FSAK during your file system normal operation. Right? You just read, write, create file. You don't need to do anything special if you are relying on FSAK. Right? But if you're using journaling, for every write operation, at least, you need to create journal. Right? If you create a file, you need to create transaction. Those are additional operations you need to perform, right? Other than what you really want to do, right? So creating a file, you need to do all of these journaling, writing transactions, creating transactions, using barriers to make sure the order is correct. Right? Those are overheads. So journaling adds overhead on every one of your normal file system operations. But that's a downside of journaling. So that's why there are so many optimization techniques that are designed to reduce the overhead of journaling. Right? The good thing about journaling is that it gives you a much better result than FSAK. Okay, it gives you a correct state, not just consistent state, any consistent state. Right? It gives you the correct state. The downside is that it does add overhead to every operation, every normal operation of the file system. Okay, that is journaling. Yeah, I think the last thing that we want to quickly go over is the I/O devices. Right? So I think this the characteristic of hard drive, and we should have mentioned this at the beginning, right, before we talk about file system. But let's quickly go through it right now. So hard disk, right, hard drives. Hard disk has a sector addressable address space, right? Meaning that each hard drive is divided into sectors, and it appears as an array of sectors, right? And each sector is typically 512 bytes, and the operation interface that is supported by hard drive is reads and writes to a sector, right? So using hard drive is very slow. And the reason is that hard drives are organized, inside the hard drive is a set of platters. And you are storing the data on platters, and these platters are organized in this way. Actually, organized in this way. This is what's inside your hard drive. So multiple disks, multiple platters, organized in this way. Okay, and so in order to read data from some sector, right? The sector is just a part of the location on one of the platter. Right? In order to read the data from one sector, you need to spin this platter and make. So there is a head that or pin that is used to read data from this platter. You need to spin this platter to move the pin or move the head to the location you want to read. Okay, so that is called seek, disk seek, and that is slow. You need to spin it, move the head to the sector you want to read, and that is why using hard drive is very slow. Okay, and yeah, so when you buy hard drives, you often see these characteristics in how many RPM this hard drive supports, right? So 10,000 RPM is about saying that single rotation takes 6 ms. So yeah, how fast it spins. Okay, right. Surface is divided into tracks, and a stack of a track across platters is called a cylinder. And the tracks are divided into number of sectors. Right? This is an example of a sector on one plate. Right? And you have a head on the moving arm that can read from each surface. Right? So the time that it takes to read data from a disk involves how you can move this head to the sector that you want to read. Right? For example, if you want to read this sector, then you need to spin the platter and essentially move the head to read this sector. Okay. Right. Reading data, right? Because you need to rotate spin the disk, spin the platter, so you have this rotation delay, and you rotate the platter to the location where your head can read the sector you want to read. Okay, and yeah, so the rotation delay and seek delay, right? So you move. Sometimes you need to move the head from inside cylinders to external cylinders, right? So this is called seek. The head also can move. Okay, that's called seek time. Right. So a time to read and write a disk includes the time to seek, and time of rotation, and then the time of data transfer. Okay, so this is why disk read is very slow. Okay, yeah, so I won't go over these detailed calculations. If you are interested, you can read this. But the point to show this is to explain why disk read is so slow, and also why reading different sectors on disk takes different amount of time. Right? It really depends on. Sometimes it depends on luck. Right? So, for example, if your head, the head is currently at this sector 33, right? Then if you just want to read the data in sector 33, then it's very fast. You do not need to do seek. You do not need to do rotation. Right? And that affects a lot of the algorithm design. Right? For example, in prefetching, right? So remember we mentioned that memory prefetching algorithm. The reason is that if I do prefetching, if I prefetch the adjacent blocks from the disk, then I do not, I'm avoiding the seek and rotation time. Right? I bring in a few adjacent blocks from disk into memory at once. Right? If these blocks, they also satisfy locality, right? They are storing the data belonging to the same program, for example, that will be accessed in the near future, then I got lucky. Right? So I bring all of them in and with very small amount of time. Okay, so these characteristics of the hardware affects the design of the software. Right? Prefetching algorithm is one example of this. Okay, that's it for today. Right? If you have answer questions, come up and write down names.